session, I would like to show you a little bit the peculiarities of time transfer and how it relates to frequency generation and transfer. So we're going to see a little bit some ideas about pseudo-random sequence generation, software-defined radio, and well, most of the most common application of time transfer is global navigation satellite system time transfer. So I'll take the example of GPS. Actually, I should have said GNSS because maybe at the end we're going to see a little bit of Galileo. So that's a little bit the outline of what I'm going to present. So I'm Jean-Michel Fried. I'm associate professor at University of Franche-Comté, and I'm working at the time and frequency department of M2ST on basically what is the impact of digital electronics for time and frequency signal generation and transfer. Okay, so what are we going to talk about in this presentation? The general outline of a presentation is what's the difference between frequency and time. And just to give you the hint of what it's going to be about, it's frequency is a narrowband signal, time transfer is intrinsically a broadband operation, and that's going to make quite a difference. Also, I would like to emphasize that everything I'm going to tell you in this lab session, if you want to reproduce at home, the hardware needed for reproducing is about €50 worth of equipment. We're going to use data collected from a software-defined radio receiver. You might have heard about this RTL SDR. You can find this for about €10 on the internet. You need a GPS compatible antenna. These are active antenna. They have an amplifier. So you will need a bias T to power the antenna, but that's about all the hardware you need. So about €10 worth of software-defined radio, €20 worth of antenna, and the bias T, and you're ready to collect data. So if you want to reproduce this at home, it's kind of a easy to reproduce experiment. We're going to see, so once I've said that we need to spread the spectrum for time transfer, we're going to see how we identify the pattern that has been transferred, and we're going to see that this is done through the cross-correlation estimator, and how we compute this cross-correlation is in the Fourier domain. We're going to see a little bit how all these satellites are broadcasting at the same frequency, and yet we can identify the message broadcast by each satellite, and that's called division multiple access, because each payload broadcast by each satellite is actually encapsulated in a unique code, and we're going to see how to do this. And to illustrate all this story, we're going to actually decode real recorded GPS signals, and we're going to see that there's a last little trick here, is that the satellites are moving along their orbit, and we need to cancel Doppler shift. So that's the outline of what we're going to talk about in the coming 2 hours. And just to raise your interest, if you don't care about GPS, what I'm going to tell you about is applicable to any time transfer technology, whether we're talking about radar, because when you want to detect a target, you're ranging between your emitter, target, and receiver. It's exactly the same story. We're using the same technology for two-way satellite time and frequency transfer. So we developed a software-defined radio modem for broadcasting time over geostationary satellite. It's also applicable over optical fibers. You can modulate your optical wave the same way you're doing this with microwave signals. So the story I'm going to tell you here is applicable to most media for transferring time. So from my perspective, GNSS is actually a set of very good quality space-borne atomic clocks, and I have access to these 70, 80 atomic clock signals. And if you have access to the raw data, so not the output of your GNSS receiver, but you actually have access to the lowest level, which is the electromagnetic wave propagating this information, you can do much more than just time and position transfer. Some of the presentation you will find in the past developments, there's been some work on how you can time the difference between the direct wave reaching antenna and the wave bouncing over, for example, a body of water, and that allows you to make a tide gauge using the time delay difference between the direct wave and the reflected wave. There's people working on analyzing the amplitude difference between the direct wave and the reflected wave, and because the reflection is intensity is related to moisture in the soil, you can make some moisture detection. One of the outputs of GNSS is is an estimate of ionosphere ionization plasma level, where it's called total electron content, the tech output. And finally, for example, when I'm monitoring glaciers in Arctic regions, people have been putting one antenna on the surface above snow and one antenna on the surface of a glacier, and the time delay between the two allows you to measure the snow thickness of a snow layer. So there's a lot of things you can do with GNSS beyond positioning and time transfer. Most of these techniques will require phase recovery, because we're going to see that the code broadcast by most of its GNSS signals are 1 megahertz, namely 1 microsecond between the messages, and 1 microsecond is the time needed for light to travel 300 meters. So the range resolution of a code is 300 meters, whereas the carrier is at 1.57 gigahertz, is 15 centimeters. So you greatly improve your resolution at the expense, of course, if you're measuring the carrier, because all the sound waves look similar to each other, you're working with an uncertainty of 1 wavelength. So phase recovery will allow you to greatly improve the resolution, but makes the processing somewhat more difficult. And we're going to address all these challenges using records from software-defined radio, because using SDR, you can actually record the file once and replay or reanalyze the data as many times as you want, and you don't need to wait for the constellation to match again the same position that you had. Beyond the scientific purpose, the educational perspective is you have a full understanding of the signal processing, and you can really understand the details and the limitations of processing. These low-cost DVB-T receivers, why are they so low-cost? First of all, because they're initially sold as digital video broadcast terrestrial receivers, so they're consumer-grade electronics. Usually when you go at SDR, the cost rises with bandwidth and with resolution. Here we have rather medium quality 8-bit resolution, but that's more than enough for GNSS. Many GNSS receivers actually only work on 2 bits, because we're going to see that the signal is well below the terminal noise. So all you would do by having more bits is sample the noise. And the other limitation is the bandwidth. These receivers are 2.4 megahertz bandwidth on carriers ranging from 20 megahertz up to 1600 megahertz. And because GPS in the L band is at 1.57 gigahertz, that's well within the operating condition of these receivers. But we only have 2.4 megahertz bandwidth, which is enough for the legacy GPS L1 signal, but that would not be enough if you wanted to address the newer signals L5, E5, or Galileo E1. So that's the reason why the title of the presentation is GPS decoding, because we would not have enough bandwidth with these signals to analyze more advanced GNSS, even though everything I'm going to tell you is applicable to these signals if you have a bit of more bandwidth with your GNSS or your SDR receiver. So my inspiration to try to tell you a little bit the outline of what we're going to talk about is this chart that you will find at the very beginning of a book of Kaibor, Software-Defined GPS and Galileo Receiver, where they show you how a satellite is generating the signal that is being broadcast on GPS L1. We're not going to talk about L2, the military band. We only focus on GPS L1, course average signal, which is the civilian signal. And you start with this atomic clock at 1023 megahertz. You're going to understand soon why 1023 megahertz. And this carrier is multiplied by 154 to get the carrier, the 1.57 gigahertz carrier in the L band. L band being selected to have little impact of a troposphere delay. Troposphere is cloud, rain, moisture in the atmosphere, and have little ionospheric impact. So the ionosphere, the upper layers of ionized plasma. So the L band is dedicated to space communication and has much less is much less impacted by troposphere. But for example, Ku or Ka band at much higher frequency, where the impact would be stronger. So all the satellites are broadcasting at 1023 multiplied by 154. So if you were just to receive this carrier, first of all, you would have a rather inaccurate information, because all these satellites are broadcasting a Doppler shifted frequency. So even though the frequency output is very accurate, your reception is poor, accuracy is poor because of a Doppler shift. And secondly, because all the satellites are broadcasting at the same frequency, you would have no ability to identify which signal was broadcast by which satellite. And if you want to position yourself on the surface of the Earth, you will need to know the position of a satellite in space, the time of flight to your receiver, and from this you can deduce by trilateration your position on the surface of the Earth. So we need to add one more information, and that's a unique identifier for each satellite. It's the Gold code from Mr. Gold, who developed this technique in the 1950s. And these Gold codes are unique to each satellite. So actually what you're going to do is generate at a rate of 1.23 mega chips per second. We're going to talk about chips when it's the code identifying each satellite. We're going to talk about bits when we talk about the payload, the actual information that is broadcast. And this 1.23 kilo chip, so 1023 kilo chip code, is encoding the carrier for a binary phase shift keying modulator. We're going to see together what BPSK modulation is. You encode on the phase, 0 phase for bit 0, pi phase for bit 1, and this is your BPSK modulator that generates the output on the L1 band CA code. Finally, the code is a unique identifier for each satellite, but there is a payload. The payload is, for example, the time offset between the satellite clock and GPS time. You never steer an atomic clock, you let it drift, because this is a very reproducible drift, so you let it run by itself, and you document to the user what is the linear and offset, so constant and linear offset of the clock with respect to your receiver, and you need to have the ephemeris to position the satellite in space, and these are all information that I broadcast in the data payload. You see that this is a very slow data rate, 50 bits per second, and you will need a few minutes to collect the full information to position yourself, because with all this information broadcast by satellite, you can calculate the position of the satellite in space and hence trilaterate your position. Notice that these information are clock predictions and orbit predictions. If you want to have what is now centimeter resolution GPS, you would not have enough resolution with this information, because these estimates are still subject to disturbances of the clock evolution or the position of a satellite due to external bodies moving the satellite from the predicted position. And if you look at the raw data that you collected, for example using SDR, you can post-process this information using not the predicted clock and predicted orbit, but the observed clock and orbit. And these information are published on the CDDIS website. So you've got, after a couple of weeks, after the observation of a satellite position in space and their clock evolution, these observations are published. And if you reprocess the data, the raw data you collected, you can actually achieve the centimeter resolution, because these orbits have such an accuracy. Okay. So this tells us what we need to solve. So we are on the other side, we're receiving the signal, and we need to go backward up to the place where you can identify which satellite broadcast and what information was broadcast by each satellite. So now let's get to the core topic, time transfer. You all know what a sine wave is. So your frequency information is a boring sine wave with only two characteristics, amplitude and frequency. And all the periods look similar to each other. This period looks similar to this one, looks similar to this one, so there is hardly any timing capability. All you can say in your frequency information is the frequency is at a given Fourier position, and you see on the spectrum there's hardly any information. If you think of Shannon's information theory, where entropy or information quantity is related to bandwidth, you see that here there is no bandwidth, there is hardly any information in a sine wave. So how can we try to improve this timing capability? we can say, for example, let's try to take 1 out of 2 periods and flip the phase. So the first period remains at 0 phase, the second period will flip to pi phase, then back to 0, back to pi. So that's a little bit better now. We have 1 out of 2 period timing capability. So if earlier you had a 10 megahertz sine wave, 100 nanosecond period, now we can separate the first 100 from the second 100 nanosecond. We have 200 nanosecond time resolution. That's a bit better, but still not very good. But what you see on the spectrum is now, instead of having just one Dirac spectral component, we have started spreading the spectrum. We've added more spectral components. So what we're going to do now is generalize the idea, and to generalize the concept of flipping the phase, instead of flipping 1 out of 2 phases, we create a random sequence of phase flipping. Now, if you have a random sequence of phase flipping, there is only one time delay, time offset, if you know this random sequence of phase flipping, where you will actually match the received signal sequence with your local copy of these phase flipping sequences. And this unique time offset will be what we need to actually do the time transfer. So if you look in the spectrum domain, now that we have this random sequence, there is no periodicity in the phase sequence. So the fact that we had discrete rays over here or spectral components means there is a periodicity. Here there is no periodicity, so now the spectrum has become continuous, and the width of the spectrum is the inverse of the time resolution. So the broader the spectrum, the better the time resolution. So that's what actually is the story about spectrum spreading, in order to introduce timing capability in addition to the frequency information that is being broadcast. Okay? So now we said we're going to imprint on the carrier these random sequences of phases, but the question is, on the receiver side, how am I going to recover this pattern? So I receive a signal S of t, and I've broadcast a pattern that I call P of t. And the question is, how can I detect this pattern in the received signal? So let us assume that the mean value of S is the mean value of t. That makes everything much easier, is 0. So the mean values are 0, so half of the samples are positive, half of the samples are negative. So if you multiply your signal with the pattern that you receive, sometimes you're going to get positive times positive is positive, sometimes you get positive times negative is negative, and on the average, you cancel out your sum of this product. So if we want to average, we're going to integrate over the duration of a pattern. So most of the time, these quantities will average out, except if you shift the pattern over the signal that you received. And if I shift the pattern by a quantity tau, and I integrate over the duration t, maybe there's a time delay when the pattern matches the copy that is broadcast on the signal, and then the negative part multiplies with the negative, becomes positive, the positive multiplies with the positive, and you see that energy accumulates. So actually you will accumulate energy if you find a tau time delay where the shifted copy of a pattern matches the received signal. And this estimator is called the cross correlation between a signal and a pattern as a function of tau. Now, if we want to estimate the timing capability of a signal, a pattern P, we actually estimate how we resemble ourselves. So what is our capability to detect tau uniquely by looking our own copy time delayed. So this is the autocorrelation. So the estimation of this quality of a signal is the cross correlation of myself with myself. And the autocorrelation will be used to assess the timing capability. I should actually mention this is a cross-correlation for real quantities, meaning no imaginary part. We will see in a few seconds that we manipulate complex values, meaning real part, imaginary part, and in this case you must remember to complex conjugate one of the two terms to match the definition of a cross-correlation. So let's have a look at what is the autocorrelation of these signals. And if you autocorrelate a sine wave, well, I told you a sine wave, they all look similar to each other. The autocorrelation of a sine wave is uniformly 1. There is no timing capability in a sine wave. All periods look similar to each other. We flipped 1 out of 2 periods, so you see that the autocorrelation looks mostly flat, even though there is some structure when we zoom in, and at least we have a bit of a timing capability, but yet you have a very strong uncertainty. You don't know if you have a 200, 400, or 600 nanosecond time delay that you detected. So it's a bit better, but still not very good. Now, when we introduce the random sequence of phases, a random sequence only looks similar to itself by a 0 time delay, tau equals 0. If you have any other time delay, the positive and negative quantities will average out, and you see that for non-zero time delays, the autocorrelation is 0, and you get only one unique correlation peak. So the time delay identification is unique, and you can actually demonstrate that the width of this correlation peak is one single sample, and the single sample is the inverse of the bandwidth of a spectrum. So you see here that using the autocorrelation, we can check that the timing capability is met with this random sequence of phase imprinted of the carrier. So let's try to put this concept, let's try to put these equations in practice. And to do this practically, I would like us to play a little bit with a piece of software dedicated for digital signal processing, which is called GNU Radio. So just to get you familiar with what GNU Radio is, GNU Radio is a set of C++ libraries, so very efficient in terms of computational speed. And these C++ functions can be called from a Python API. So we actually have the best of both worlds. We have the ease of programming in Python, and we have the speed of a C++ library. And GNU Radio is a free open source software, meaning you can legally install it on your computer, and open source, you can read the source code to learn from others and possibly correct bugs if you find them. So GNU Radio comes with a graphical user interface, which is called GNU Radio Companion, and that allows you to generate Python code out of a graphical assembling of blocks. So to go a bit faster during this lab session, I prepared for you quite a few flowcharts, but still I would want you to become a bit familiar with GNU Radio and see how much more enjoyable it is over NumPy or MATLAB programming, because we're going to see that GNU Radio makes our flowchart interactive, so much more fun to play with. So what we're going to do before running the flowcharts I prepared for you is let's create a new cute graphical user interface, and let's start with this blank flowchart with no processing blocks. Whenever you're doing discrete time signal processing, there is one quantity that will determine all x-axis of your charts, and that's the sampling frequency. The sampling frequency of your discrete time signal processing is either in the time domain, when you have your voltage continuous, the time steps when you sample the data. So these time steps Ts are the inverse of the sampling frequency. So whenever you have your samples, assuming you have not lost the continuous stream of data, you can identify the time at the timestamp of each sample just knowing its index in the sequence. But what's very important is when you take the Fourier transform, when you get into a frequency domain, now this quantity, power as a function of frequency, will be scaled between minus the Nyquist frequency and plus Nyquist frequency. So whether you're in the time domain or whether you're in the frequency domain, a core quantity is the sampling rate. Now, at first, we're going to work only with synthetic data, so the sampling rate is just arbitrary, something with respect to 1. If you have real hardware, as we're going to do by the end of the lab session, you need to inform GNU Radio what was the actual hardware sampling frequency. And because this is all Python programming, you actually have a default variable which has been defined by GNU Radio, and the default value is that this quantity is equal to 32,000, random value that was selected. So what you see here is a Python expression which says the sampling rate, which is something that we're going to use throughout our flowchart, is randomly equal to 32,000. You could set it to anything else depending on your actual simulation. Okay? So that's the first empty flowchart. I just explained to you why we have this first variable that has been defined. And then in the naming convention of GNU Radio, you generate data, so it's a source. You process the data, so you have a few processing blocks. And you have sinks, which are the output of your processing. So the naming convention is you start with source, you have a processing chain, and you end up with a sink. So let's have a look at what are the sources that we have available. So if you go on the magnifying glass over here, and you type source, you're going to see a few of these sources. Of course, you don't want to go through all these processing blocks. And you see here that we have a few of these sources, amongst which we have a signal source. So if you double click on the signal source, or if you drag and drop the signal source into your flowchart, you see here that we open the signal source with the usual characteristics that you expect from a signal generator. You have the waveform. Here it's a sine wave. It could be triangle. It could be a square wave. You see that you have usual characteristics, a frequency, an amplitude, and a phase offset. So your signal generator is providing all the quantities that you expect, your signal source is providing all the quantities you expect from a signal generator. But then you realize here that these are complex quantities. Complex in the sense there is a real part and imaginary part. Why is GNU Radio asking you to manipulate complex quantities? When you record the information, you have an antenna. This antenna signal is possibly amplified, and the signal that is coming to your antenna is centered on a radio frequency band, centered, for example, on FC. This is offset at a radio frequency band for multiplexing the radio frequency spectrum, but when you want to analyze the content, when you want to analyze the modulated signal, you need to bring it to 0 Hertz. So you need to shift the frequency band back to 0 Hertz. And a 0 Hertz centered spectrum is called at baseband. So how do you transpose a frequency? Well, because how do you go from exponential of j omega t to something close to 0 Hertz? You would multiply with exponential of omega ct, and you see that the multiplication will create j omega minus omega c t. So you see that frequency transposition is achieved by multiplying. So multiplying is something that you do with a multiplying symbol, a mixer symbol, okay? So the frequency transposition from radio frequency band down to baseband is achieved by mixing, multiplying in the digital domain or mixing in the analog domain, the incoming signal with an oscillator. And this will bring you something that you sample at a sampling rate, which is the same FS that we had over here. Now, if you do this, you start with a real voltage, you multiply with a real oscillator. Well, when you multiply two real quantities, you end up with a real quantity, which you sample. And what is the property, what is the spectrum, what is the characteristics of a spectrum of a real quantity? The spectrum of a real quantity is an even function. The magnitude of the negative frequencies is the negative component is the complex conjugate of the positive, so the magnitude of the negative spectral component is the same as the magnitude of the positive spectral component. So if you just do this, you're going to end up with an even spectrum, and we lost half of information because no one said that the spectral components below the radio frequency carrier must be the same as the one above. So actually we need to find a trick to recover the negative part of the spectrum, and if you have a non-even spectrum at baseband, it necessarily means that you must have a complex quantity over here. The only way to have a non-even spectrum at baseband is because you have complex information. So what is a complex information? Well, you know that exponential of jx is cosine of x plus j sine of x. So the imaginary part with respect to the real part is shifted by 90 degrees. The difference between a cosine and a sine is rotating by 90 degrees. So actually you cannot just run a simple scheme like this one to record data and keep all the information. What you will have to do is take your antenna information, possibly amplified. As earlier, we're going to multiply with a local oscillator at a frequency Fc. And this will bring us a first information which we sample at a sampling rate Fs. But with this, we said we only have a real quantity. So we need to duplicate this path, and we duplicate by generating a second quantity shifted by 90 degrees. How do you shift by 90 degrees? You take your oscillator, quarter wavelength, and you multiply with the same signal but with the second quantity shifted by 90 degrees. And now you sample this guy as well, also at Fs, and you get a second output. These two outputs, that's your real part because you multiply by your cosine. This is called identity. And the second one is shifted by 90 degrees. It's a quadrature. So you have two components at the output of your software-defined radio receiver, which are I and Q. And I and Q match your usual complex quantity algebra, meaning that the amplitude is I plus jq magnitude, which is square root of I squared plus jq squared, and the phase is the arctangent of q over I, as you would expect from a complex algebra. Okay? So you see that naturally, whenever you're processing software-defined radio data sets, you will manipulate complex quantity most of the time and hardly ever real quantity, real in the sense no imaginary part. So that's the reason why by default GNU Radio tells you let's use complex quantity. Actually, you could set to float, which is a real quantity, or even to integers, 32-bit, 16-bit, or 8-bit integers. And in order to identify the color convention, you see here we have a blue output. These blue outputs, you can check in the help types. You have here the colors coding. You see that everything that is blue is complex quantity, real plus imaginary. Everything that is orange would be a real single precision floating point number. And before the end of this tutorial, we're going to see that we will manipulate integer 8-bit, because if you have a software-defined radio receiver that streams 8-bit outputs, it's natural to store in a file the 8-bit quantities and to stream in the flowchart these 8-bit values. Okay. So you see here you have a color coding of the value that is being streamed. So now that we solve the source description, let's go to the sink. And when you look at the sinks, you have many, many types of sinks, but we would like to work with graphical interfaces. So you see now that we have various sinks, and in the Qt graphical user interface sinks, we have a few items. Somehow the GNU Radio developers decided not to call an oscilloscope and a spectrum analyzer, but they say that an oscilloscope is a time sink and a spectrum analyzer is a frequency sink. So let's select these guys. Let's select an oscilloscope, time sink, and let's select a spectrum analyzer, which is a frequency sink. and we can connect them together. So we run a wire, an arrow, between the output and the input. So here we have a perfectly valid flowchart, and if you look, the arrow here is highlighted, so we can actually execute this flowchart. Don't do so, because this is a flowchart with only virtual synthetic data. You see that there is no clock source or there is no clock sink. It's all virtual. There is no hardware in this story. There is no sound card or there is no software-defined radio emitter. If you were to run this flowchart, you would tell the GNU Radio scheduler, generate 32,000 samples every second, but no one told the scheduler what 1 second is, because there is no clock in this flowchart. So if you were to run this flowchart, your CPU would crawl to a halt, because GNU Radio is pushing as many data as it can. It doesn't know what 1 second is. So when you have a flowchart with only virtual blocks and no hardware, it's important that you have no hardware, otherwise there is timing conflicts. You need to add one more block, and like on your car, if you want to go faster or slower, you have a throttle. And the throttle is a block which you use only if you have no hardware in your flowchart to tell the scheduler, this is more or less 1 second. More or less because it's 1 second defined by the operating system. We're working on a multitasking operating system, so the timing resolution is not very good, but at least it tells you more or less what 1 second is. And you just connect this guy in parallel to the others, despite there is an input and an output. You can actually, it's documented on the GNU Radio tutorial, that the throttle block does not need to have the output connected, and it's actually somewhat more efficient to just have an input and no output, so you don't have to stream the data. And actually the throttle block will backward tell the signal source, I received 32,000, now slow down, stop sending data for a second, and only 1 second later will the throttle block allow the source block to stream again a batch of data, and the other blocks will be somewhat scheduled by this throttle block. Okay? So now that we have this, we need to save. So you just randomly save any name that you want. Remember, these are all Python variables, so just make sure that you use the usual characters, no awkward, so nothing starting with a number, no awkward French accent or unusual characters. Just use your usual naming convention that you would use for a file name. And once we've saved the flowchart, we can actually execute. And when you're executing this flowchart, you see here what it looks like. So we've got on top the time domain, and we understand now that there are two quantities because you've got I and Q. Never tell an engineer that you measured an imaginary voltage. Imaginary voltage is a real quantity shifted by 90 degrees, so you've got two voltages, I and Q. And in the frequency domain, you have a unique spectral component which is shifted by the 1 kilohertz. GNU Radio writes 1K, but when you enter the value, it's a Python expression, so you must write 1000. So far, we have our spectrum analyzer, we have oscilloscope, you have a generator, but this is no more fun than MATLAB. It's the same thing. We have a static simulation. How can we make this more fun? Well, you see here that we have all the characteristics of our signal source. And let's say that this guy, the frequency, we don't want it to be a static variable, but we want it to be a variable, something that is user tunable. Okay, so let's say that this frequency, we don't want it to be 1 kilohertz fixed, but we want it to be a user tunable variable, so frec. So now if I do this, GNU Radio is going to complain because it says you assigned a frequency value, but you never defined this frequency value. So how do we define the variable? Well, as opposed to selecting a static variable over here, we can actually select a user tunable variable. And when you want to tune a frequency in a given range, well, it's a cute graphical user interface widget, which is called the cute GUI range. And if you select a range, you will be able to manually tune the variable to a given range. So if you double click on the cute GUI range, on top you see here we have an identifier. this identifier is actually the Python variable name that you define with this slider. And what we want is we want to define here the same variable that we're using over here. This is how you match these two processing blocks. So we're going to say that the queued range frequency is the same as the frequency that we're using over here. So you see that we have a minimum value, 0 Hertz, DC component. We have a default value, 50 Hertz. What would you select as a maximum frequency for this block?
Half the sample rate.
Right.
16K.
So 16K. Do you agree? So it's a Nyquist frequency. Your spectra, when you sample at Fs, are going from minus Nyquist frequency to plus Nyquist frequency. So minus half a sampling rate to plus half a sampling rate. Now, in this case, do not write 16,000. Because indeed, sample rate divided by 2 is 16,000. But if I write here a static quantity, if I were to change this variable here, I want to spread the information on all the processing blocks. And these are all Python expressions. So you're allowed to write sample rate divided by 2. So that when you change the sample rate, say you want to use the same flowchart, but replace the synthetic blocks with real hardware, well, you want to make sure that these values remain consistent throughout the flowchart. So you put the expression rather than the quantity. And of course, when we accept, you do see actually that it calculated 16K. But if I change this quantity, automatically this one will be updated. And so the fun thing, and the reason why GNU Radio is so much superior to MATLAB when you want to do some signal processing, is that now I can actually interactively play with my flowchart, and I can change the parameters of the flowchart. So actually this might look more like fun, but for example, when I'm receiving a satellite signal, and I need to tune few parameters such as a loop bandwidth or a gain, well, if I hear the satellite signal or if I see a constellation plot and I see that the constellation is not well tracked, I can actually interactively play with my flowchart as the data are streamed, the IQ stream are collected by the software-defined radio receiver, and I watch the output on the screen. So actually this interactive interaction with your flowchart is somewhat useful whenever you want to to tune the parameters of a flowchart when you're receiving a signal. Okay, so I hope you're all convinced that GNU Radio is a lot of fun for testing signal processing concept. And we just spent quite some time discussing that what we want to perform for analyzing time transfer is correlations. So let's select the correlation block in GNU Radio. And so this way we will be able to assess our understanding of how a correlation is performed. The amplitude of the Fourier transform depends on the normalization that you select. So when you might know that under different pieces of software, some people will define the Fourier transform as 1 over n, the sum of your signal that you have 2 pi fk times the index k. Some other software will write this as sum of xk exponential of j2 pi fk k. And some other software define this as 1 over square root of n, sum of xk j2 pi fk k. The only thing that matters is that when you then take the inverse Fourier transform, in this case it would be sum of xk minus j2 pi fkk. I'm not going to write all of them. In this case, your inverse Fourier transform is where you would put the 1 over here n over here. And in this case, you would put in the inverse Fourier transform the 1 over square root of n over here. So you have to be careful whether you're working with MATLAB, NumPy, or GNU Radio, your normalization will not always be the same. The only thing that matters is that the inverse Fourier transform of the Fourier transform must be identity. But the normalization factor will depend on your convention. So there is no easy answer on the relationship between the magnitude in the time domain and the magnitude in frequency domain, to my knowledge. So we said we want to do correlations, and so we search for the correlation block. So let's search for correlate. And the problem is if you search for a correlate block in GNU Radio, we want to have something that correlates a signal with a pattern which is recorded, and there is no such block. There is no correlation block in GNU Radio. You actually have a pseudo-number correlator, which is a header correlator, a digital correlator, but that's not what we're looking for. We're looking for something that will correlate two signals, a pattern P with a signal S. And there is no such feature in GNU Radio. So why did I waste your time introducing GNU Radio if there is no correlation processing blocks? Let me just spend a few seconds on another aspect of another estimator than the correlation. I just want to introduce the convolution. The convolution is defined as the convolution between two quantities is the integral of s of t. In a convolution, the second term is tau minus t dt. And do you know your convolution theorem? What is the Fourier transform of a convolution of S and P? Is Fourier transform of S multiplied by Fourier transform of P. Now, the reason why people very often use this expression of a convolution is that thanks to the fast Fourier transform, which uses the symmetry of the trigonometric functions, instead of having an n squared complexity algorithm, you have an n log n. And for large n, it's much more efficient. So why am I wasting your time defining the convolution theorem on this estimator when we want to talk about correlations? You see the close link between a correlation and a convolution. The only thing that changes is the direction of time. So we can express something about the cross correlation. But now the time has been flipped in the second term. How do you flip time? How do you go from exponential of j 2 pi ft to exponential of minus j 2 pi ft? What is the operation that will allow me to go from one to the other? I take the complex conjugate. So the cross correlation of the Fourier transform of a cross correlation is the Fourier transform of S multiplied by the Fourier transform of P complex conjugate. So in other words, when you want to compute the cross correlation between S and P, you take the inverse Fourier transform between the Fourier transform of S and the Fourier transform complex conjugate of P. Okay? This is not only interesting for GNU Radio because it means that we can run the correlation even if we don't have a correlation block. But the reason why I'm emphasizing this is if you read GNSS decoding software, and the best one you can read is GNSS SDR from Carles Fernandez and his team in Barcelona Technical University. If you read GNSS SDR, you'll see many, many Fourier transforms everywhere. And if you have not realized that you're computing the correlation in the Fourier domain, you wonder why do we have all these Fourier transforms everywhere in the SDR processing of GNSS signals. And that's the reason. The reason is it's much more efficient to express the cross correlation in the Fourier domain because you have an n log n algorithm in the fast Fourier transform rather than the n squared algorithm, n squared complexity, because you have n multiplication that you must repeat for the n possible values of tau, the n values of a delay. Okay. So now that we've done this, let's go to the first example over here. And this first example I prepared for you, I just prepared it because so we don't waste too much time searching for the blocks. But it's exactly what we just said. You take a noise source, so a non-repeating sequence, and you throttle because you want to slow down the CPU. And remember, the objective of this lab session is to measure delays. So you introduce a delay. This delay here is a quantity we want to measure. The delay is defined by a slider. So I'm going to use a slider to move the time delay. And if you want to measure a delay, it's always a delay between something and something. A delay doesn't make sense if you don't refer to something else. So you need to keep a reference. You need to keep track of what is the signal that you broadcast. And you have the time delay copy of the signal. This is also what I use when I'm developing noise radar. When you do noise radar, you generate a noise. you're the only one to record the copy of the noise, so no one else who's looking at the spectrum can know that you're broadcasting a signal for ranging targets. But because you know the noise signal that you broadcast, you can look at the backscattered signal from the targets, and by cross-correlating, you can detect the various backscattering reflectors, which are radar targets. So in radar naming convention, this is the reference channel, this is the surveillance channel. And you have this noise, this random sequence that you're generating. You keep track of what you generated. You take the backscattered signal, you multiply, conjugate, and you inverse Fourier transform to get back into the time domain. The only trick in running this flowchart is when you calculate an integral, you cannot run this on a stream. GNU Radio is stream-based, meaning it will generate data one after the other, and you should not make any assumption on the size of the batches that feed a processing block. But if I want to take a Fourier transform on 1024 sample, I must make sure I've collected at least 1024 sample to calculate the integral. So this block here, the stream to vector, will accumulate samples until we have enough data from the stream to accumulate one vector of length n, and only then are we going to feed the fast Fourier transform block, which knows it's got more than 1024 inputs, and then it can run its FFT. So the only trick is you have stream inputs, you convert the stream to a vector, you Fourier transform the vector, you multiply, conjugate the vector, you inverse Fourier transform the vector, you go back from vector to stream, and then you plot the stream output, okay? So if you run this, we have on the bottom the output of the Fourier transform. You have here a slider, and if you move a slider left and right, you introduce a delay, and you see that surely enough, the inverse Fourier transform of a product of Fourier transforms of incoming, so the reference signal and the surveillance signal, the correlation peak is tracking this time delay that I introduced with this delay here. And if I look on the waterfall, because I can actually display the time evolution of a delay, you see on the waterfall how whenever I introduce this delay here, you see that the waterfall accurately displays the time delay. So the cross-correlation, usually when we run the cross-correlation for time transfer, you don't care about the magnitude of a correlation peak. What you're interested in is the position, so the time delay, the time offset of a correlation peak. So this demonstrates how we can actually run the cross-correlation calculation in the Fourier domain. But in real life, what are we going to get? In real life, we are, with our receiver, getting the information from all the satellites flying overhead, and all the satellites will be broadcasting at the same frequency. So what we get on the receiver is the sum of the voltages of all these satellites. And we want to decode each satellite individually. We've seen that the cross-correlation is expressed as a Fourier transform, and the Fourier transform is linear. What is a linear function? A linear function means that f of ax plus by is af of x plus bf of y. So if we have a sum of multiple incoming voltages, when we run the correlation, well, you can actually say, okay, I got a sum of two satellites, but this is similar to processing the first satellite and the second satellite individually. Or if I come back to my noise radar example, I broadcast a signal, I've got multiple targets, and even though I want to detect all the targets that backscattered energy, I only need to take one Fourier transform because the Fourier transform is linear. And I don't need to run as many correlators as there are targets. So just to illustrate this concept, I prepared for you this flowchart, which is exactly the same as before. You see that we have noise generator, throttle block, stream to vector. This is the reference channel. And you see now that I delayed 3 times the noise output. And these three delays, so I don't have three sliders to move, you see that these three delays are defined by a signal source number 1, which is a triangle wave, a signal source number 2, which is a square wave, and a signal source number 3, which is a cosine, a sine wave. So what I'm going to do is I have three targets, and these three targets will have a time delay shaped as a triangle, as a square, or as a sine wave. And yet, even though I have three targets backscattering the information, you see that the receiving antenna, the surveillance antenna, only receives the sum of the voltages of all the oncoming signals. And when you want to detect all the targets, you only take a single Fourier transform on your surveillance antenna. You take the Fourier transform of a reference antenna, multiply, conjugate, and go back to the time domain. Okay? So you see that by using the linearity of a cross correlation, if you receive the sum of multiple targets, or if you receive the sum of multiple satellites, each one of these correlation peaks is actually the time delay introduced by a different target. And if you look at the waterfall, you clearly see that one target is shaped as a triangle delay, one target is shaped as a sine wave delay, and the third target is shaped as a square wave delay. Okay? So the linearity of a cross correlation means that even though our receiving antenna will get the sum voltage from all the broadcasting satellites, we still can, or if I'm talking about two-way time transfer, all the NMIs in Europe are broadcasting at the same time a two-way time transfer signal. The satellite Telstar 11N is rebroadcasting over Europe the sum of all these signals that have been incoming to the satellite, and yet you are able to identify which NMI has broadcast which signal, and you can time the time of flight from this broadcasting signal. All good so far? So now we've seen how GNU Radio allows us to have fun with these various concepts. And if I go back to my slides, so this is the flowchart that we just saw together. So if you, in the supporting material, you've got a reminder of the relationship between convolution and correlation. This is the flowchart that we just played together, and it looks impressive at first, but now you understand that this is just copy-pasting the same flowchart 3 times with the three possible delays, but there's more and more blocks. But you see that when you do it step by step, you can actually understand nicely how this is all working. Now I need to introduce one more concept, the concept that these satellites are located 20,000 kilometers away. These are medium Earth orbiting satellites. They are MEO satellites. And a GPS satellite is broadcasting 50 watt, 47 dBm. 50 watt is a light bulb. So you've got this light bulb 20,000 kilometers away, and yet through the power of signal processing, we can actually detect this information on the ground. So, of course, if this faint signal has propagated all this way to your receiver, this signal will be very weak. Actually, it's 10 decibel below terminal noise. What would you do if you want to extract a signal from noise? What is the mathematical operation you would use to get rid of noise? Averaging. So what we would do is say, let's average out this multiple time evolution copies of a signal, so noise slowly lowers until the signal comes out. So here you have a sine wave, and the sine wave is polluted with noise, and you say, let's average out the noise, so let's run a sliding average. And you get the blue curve over here. So yes, the blue curve, you see that you managed to extract the sine wave and get rid of the noise. But by doing this, you actually spread the information over a longer duration. The longer the sliding average duration, the better your noise cancellation capability, 1 over square root of n, with n the samples over which you average. But by doing this, you've spread the information. And this is exactly the opposite to what you want to do with GPS. A GPS signal wants to transmit time, not to spread information over a longer duration. So yes, we managed to remove noise, but on the other hand, we spread the information. How can we avoid spreading the information while still cancelling noise? Well, what you do is actually you take a sine wave. The reason why information has been spread is that this sine wave looks exactly like this one, which looks like exactly like this one. So when you run your sliding average, you see that you actually accumulate energy when this guy meets this one or this guy meets this one. If you want to avoid spreading the time information, what you must do is use a sine wave with varying frequency. A sine wave with varying frequency is called a chirp. A chirp is something where the initial frequency is not the same as the final frequency. And by doing this, when you run your sliding average, this sine wave, which does not have the same period as this one, when you multiply this guy with this guy, they cancel out. When you multiply another sine wave with another sine wave, they cancel out. The only time your sliding average will have an accumulation of energy that does not cancel out is when you have an exact match between the noisy signal and the average signal. And what you see here is a black curve. Now when we run the sliding average, so the denoising procedure on the chirp, only when the chirp overlaps do you accumulate energy. Now you see that the black curve has, similarly to the blue curve, cancelled the noise. But now you get a unique correlation peak, and the correlation peak width is determined by the bandwidth or the spreading of your chirp. So we have these two dual requirements on the signal that we broadcast. On the one hand, we want to have averaging duration. So we want a long duration to average out the noise. But on the other hand, we want to have some bandwidth because by using a broader signal, a broadband signal, we avoid mismatching the end of a signal with the beginning of a signal, and so the broader the bandwidth, the narrower, the sharper the correlation peak. So you've got these two quantities, so this is in seconds, this is in hertz, and this allows you to write an estimator of how good your signal is for time transfer, and this estimator is called the pulse compression ratio, which is the product B times T. So you see, you multiply seconds with hertz, you have a unitless quantity, and what you can actually demonstrate is that the product BT is the SNR improvement, the signal to noise ratio improvement by correlating. So when you run the correlation, you receive the signal, you know what is the pattern, you get a signal that is very weak, well below the noise. So if I look at what this means, you might get in power a GPS signal. So your GPS signal, well, when you look at the standards, it should be at least minus 130 dBm. So it's going to be something like minus 120, minus 130 dBm, depending where you're in this free space or in the canopy. And what you can demonstrate is that over the 2 megahertz bandwidth of your GPS signal, the terminal noise integrated over 2 megahertz is minus 174 dBm per hertz multiplied by the 2 megahertz bandwidth is going to be something like minus 111 dBm. So you see that your GPS is 10 to 20 dB below terminal noise. If you look at the spectrum of a GPS signal, you're not going to see it. It's just a slight bump above the background. But thanks to the pulse compression ratio, we can actually accumulate the energy in the correlation peak and raise it above the terminal noise. How can I estimate the gain from a correlation? We just say it's a bandwidth multiplied by duration. So this was an analog definition of a pulse compression ratio, but in 2025 we're thinking of digital electronics. What is the bandwidth? Well, the bandwidth is actually the number of symbols per second that you're sending. So this would be your n chips per second data that you're sending. And the duration, well, the duration is determined by the number of chips in your code. So actually, the product B times T in a digital domain or in a digital implementation of a code is equal to n, the number of chips in the code that you're broadcasting. So what you see is that the longer the code, the longer the random sequence that you're sending, the better your signal extraction capability and your noise cancellation capability. So for example, in GPS legacy signal, so in the GPS L1, the number of chips in the code is 1023. So if I take 10 log of 1023, that's about 30 dB. So this means that when I run the correlation, my minus 130 dBm signal is rising by 30 dB. That's your pulse compression ratio of GPS. And you see that I get to something like minus 90, minus 100 dBm, which is well above the terminal noise. So thanks to the pulse compression ratio factor, which defines the signal-to-noise ratio improvement, the GPS signal that was hidden below noise now rises above the terminal noise, and I can run the decoding. Okay.
Is terminal noise the same in every case?
As long as you're on the surface of the Earth, yes. But if you take a radio telescope facing space, then the terminal noise will be much lower because temperature of space is not room temperature, it's 4 Kelvin. So actually, you don't take the calculation as 4 Kelvin because you have a bit of backscattered energy from the side of your parabola. So usually when you literature about terminal noise of a radio telescope, you take something like 40 Kelvin. But so this terminal noise at room temperature will be always minus 174 dBm per hertz. If you do the calculation for radio telescope facing towards space, it will be somewhat lower. Okay? So minus 174 is kb multiplied by T in Kelvin, which is 300 Kelvin. That's how you get the minus 174. Okay? All good? So we understand now the pulse compression ratio. So we can go through this with multiple examples. This is just a quick demonstration. Why does GPS use a pseudo-random sequence? Because if you were using a sine wave, the same shape as the GPS signal, yes, you would cancel out noise, but you would spread the information over a long duration, whereas with a random sequence, you have just a sharp correlation peak. So that demonstrates the concept of GPS signal generation. We're slowly getting there. We're going to get to the GPS. The last item I need to introduce is the fact that so far, how did we generate the non-repeating sequence? We said we generate noise. I told you if I'm doing noise radar, I generate a random sequence, Gaussian distributed noise, and because my emitter and the receiver are co-located in the most static radar, I can just have a loop back between one channel of my radio receiver and the broadcasting antenna, and I record any noise that I'm generating. This is fine for noise radar, but if I wanted to do this with a satellite, I would need somewhat like a 20,000 kilometer cable to the satellite to know what is the random sequence that is generated, and that would not be convenient. So I need a reproducible analytical way of generating a non-repeating sequence, because this is what random means. It means I don't have a spectral component that defines the repeating period. So I need a non-repeating period that can be generated algorithmically without having to record the noise generated by the radar. And one sequence that is well known from centuries is what Évariste Galois worked on when he wanted to identify means of generating non-repeating sequence, and these are called the Galois linear feedback shift register, the GLFSR. What is a GLFSR? It's a shift register, meaning you've got bits one next to the other, and every clock cycle you take all the bits and you move them to the right. So the guy over here is dropping out. This is the output that you use to modulate your BPSK modulator. And all the bits have been shifted to the right. And what Galois demonstrated is that if you wisely select the position of the taps, meaning the 2 bits that feed an XOR gate, and you feed the output of the XOR back into the linear feedback shift register, then an n-bit long shift register will generate a sequence that does not repeat before 2 to the n minus 1. 2 to the n is the number of values that you can generate with this register, but there is one that is forbidden. because if you have all zeros, you see that 0 XOR 0 is 0, and you would loop back the 0 condition. So 0 is forbidden. 0 is a forbidden state, and this is why the GLFSR over n bit will generate 2 to the n minus 1 values. I would be hard-pressed to demonstrate this right now. And how would you select the tap position? Well, even if I cannot demonstrate to you how to select the tap position, I can give you where to find the information. And Professor Koopman at Carnegie Mellon University tabulated for us all the possible taps for all shift registers from 4 to 64-bit long registers. Now remember, 2 to the 32 is 4 billion. 64 bits is 4 billion squared. This is a very long sequence that never repeats. So what's beautiful is that nowadays, if you have actually enough computational power, you just run a GLFSR, and you see that these are just XOR gate on a shift register, so an FPGA will easily fit all the resources needed to run even a 64-chip long GLFSR. And for example, in our two-way satellite time and frequency transfer, running at 2.5 megashifts per second, we managed to easily fit in FPGA a 2.5 million non-repeating sequence in the FPGA and run this in real time. So if you have a look, for example, at the 7-bit long register, you see that we have 18 possible maximum length sequences. So this means that you can have up to 18 satellites, and these 18 sequences will not repeat in the same way, meaning that if you cross-correlate the satellite A with the satellite G, so if you cross-correlate the sequence of I with the sequence of J, you get a delta ij, meaning you get a non-zero value if you have the right sequence, and you get zero value if you have the wrong sequence. Okay? So you see that the more chips we have, the more satellites we can put in space. And for example, for the 1023 bits of the gold code, you actually have up to 60 possible solutions, and the gold codes are actually more fancy than this because they're two intertwined GLFSR 10-chip long, 10-bit long register GLFSR, so of 1023 chip long codes. So you see here that if we go on the 7-bit long, these are hexadecimal representation. Every time you have a 1, it's a tap position. Every time you have a 0 in the hexadecimal sequence, you have no tap. And you see these are the 18 possible sequences where you would want to put your taps feeding the cross-correlation. So again, how can we apply this in a practical manner? So how can we run this in GNU Radio? So let's go to the next demonstration. So now the right-hand side, I don't need to tell you anymore how it works. So you got your sequence, you take the Fourier transform, multiply conjugate, inverse Fourier transform, vector stream to get back to the time domain, and you've got your correlation. So this, now you understand, is all the cross-correlation. That's easy enough. But now on the left-hand side, instead of having the noise generator and the time-delayed copy, you see that now we have two GLFSR sources. One parameter, the degree, is the number of bits in the shift register. We say that it continuously repeats, and we take what is the taps position, so what is the mask. And if you look at one of these blocks, you will see that actually we take the hexadecimal expression of a tap position, and this 0x60 that we're putting here is the same as the 0x60 that we just saw on the website of Professor Koopman. So that's the same 60 that you have over here. Okay. And once you've selected your GLFSR, you can actually say, okay, let's try to see if on the ground I can detect a spaceborne satellite, or if I'm searching for the wrong satellite, whether my cross-correlation will cancel out. So if you run this flowchart, on the top, you get the time domain evolution of the, this is the time domain sequence. It's not super interesting. This is the cross-correlation output, and this is a spectrum. So you see I'm plotting the spectrum of the GLFSR. You see no sharp spectral component, so it's non-repeating. I indeed selected a maximum length sequence. I was not mistaken in selecting the taps. And this is a cross-correlation. Does anyone have an idea why I have multiple correlation peaks? What's the reason for having so many correlation peaks and not just one, as I told you? If you look at the flow chart, what determines the fact that I have many correlation peaks? The GLFSR I selected here is 7-bit long register, meaning it never repeats over 127 samples. But the correlation I did is over 2048 samples. If you think in terms of radar, this is called the pulse repetition interval. The pulse repetition interval in a radar tells you what is the maximum range of a target that you can unambiguously detect. If you send pulses too short, one after the other in a radar system, and you've got a very far away target, you cannot say if the backscattered echo is from your first pulse that reached a very far away target or the second pulse that reached a nearby target. So pulse repetition interval tells you what is the maximum distance before you launch a new pulse for probing the environment or surrounding your radar. So here you see that I selected a rather short pulse, which repeats every 127 samples, but I did a correlation on a much longer duration. And because the pulses repeat, I have an ambiguous time delay detection, because you see here that I get all these correlation peaks, which are actually, if you zoom in, you see that the first one is at 8 milliseconds, the next one is at 135. So indeed, I have 120 samples between these two correlation peaks. So the peaks could repeat every 120 samples. And to answer the question about aliasing, this is where you see aliasing. It's because we calculate the correlation in the Fourier domain, and the windowing function is not perfectly canceling the side lobes. We have a bit of aliasing, and that's this leftover correlation. Okay? So I hope now that you have a better understanding about how we can detect all these satellites. All these satellites are broadcasting a known pattern. And only by correlating, no, because I haven't shown you yet that we can cross-correlate, but with a wrong satellite. So what we've seen on Professor Koopman's website, for example, you have 65. 65 is another maximum length sequence. But what happens now if I cross-correlate satellite number 60 with code number 65? So I generated two maximum length sequences, but now I'm trying to detect the wrong satellite. It's not the one that is broadcasting that I'm detecting. And now you see that your correlation does not show any correlation peak, okay? You've got a leftover background, which is 1 over n, the number of chips in the code. But you see that there is no sharp cross-correlation, meaning indeed that the cross-correlation of a satellite I with the local copy of a code number j is giving correlation peak if I equals j, and a background noise 0 if I is different from j. We generate, the codes we generate are using a shift register that is 7-bit long. So we said the size of the pattern, or the length of the pattern, is 2 to the 7 minus 1. That's 127 chip long. And I took the Fourier transform over 2047 samples. Okay, 2048. So, and in these 2047 samples, we've selected that the pattern repeats. So it means actually here you've got the pattern, then it repeats again, and so on every 127 sequence. And when you're doing the correlation, you're running one copy over the other. So it means that, yes, you correlate when you're like this, but you also correlate when you're like this, and you also correlate when you're like this. So what you're seeing is all the shifted copies of a code by 127 will run the correlation, because I selected a correlation length longer than the pulse repetition interval, which is given by the chip length of a code. All good? So, what is the last step? So now we're convinced that we have a correlations. And what is the last step we must go through to complete the decoding capability? So just let me mention that previously we used to perform this presentation with analog hardware, and actually if you look, this is all developed. GPS was designed in the 70s, running in the 80s. So of course these are all using technology that are quite easily accessible. So you can actually buy shift registers off the shelf. You have XOR chips off the shelf. Now in 2025, you would no longer do this in discrete components. You would run this inside your FPGA. This is what we're doing when we're doing noise radar. You run the pseudo-random sequence in the FPGA, and you can actually feedback on your reference channel the sequence that you broadcast. And now we're doing it with GNU Radio. So that's how you can actually play the same story in different media. So now we need, that's what we saw together. So now we need a final step before understanding exactly how GPS is going to be completed. So the last issue that we need to solve before we can actually decode a real GPS signal is the fact that all this information that we've been talking about so far are imprinted on the phase of a carrier. So if you look here at this chart, you see what is binary phase shift keying. So in BPSK, you have your sine wave, your carrier. This is a bit 0. Then you see that the phase flips. So now we have a bit 1, another bit 1, then the phase flips again. It's a 0 again. So in a binary phase shift keying, BPSK, the phase can have two possible values, 0 or pi. 0 encoding bit state 0, pi encoding bit state 1, for example. And on the other hand, if you do the mixing on the ground, you will recover the phase by getting rid of a carrier. You remember, we do the multiplication. We bring the signal from radio frequency band back to baseband. And on the baseband, we get the phase on the output. However, we have a bit of an issue here, because these satellites are in orbit, meaning they keep on flying along their orbit. And they fly at a given velocity, which means that I have a projected velocity towards the user, and this velocity vector will induce a Doppler shift. So even if on the ground you had an atomic clock, which you usually do not in your radio frequency receiver, on your SDR receiver here, you have a TCXO, a crystal oscillator, which will usually be off by a few ppm or a few tens of ppm. And even if you have an atomic clock on the ground, you would have a Doppler shift of a spaceborne satellite. So what does it mean? It means that the signal that you receive ideally would only include the phase, but it's actually something, we forget about the amplitude because it's all about the phase. So you actually have something that is a leftover delta F plus j phi of t. And this phi is this phi, which phi equals 0 or pi. So you have a leftover offset frequency delta F that you will never able to cancel, or not during the acquisition phase, because either you have a very good clock and you have a Doppler shift leftover, or you have a frequency offset between your local oscillator and the onboard oscillator. So what does this mean? It means that if I plot the phase as a function of time, I would want something that looks, for example, like this. That would be my phase sequence equal to 0 or pi. But because we have a leftover frequency offset of delta F, you actually have a slope which is 2 pi delta ft, and your phase is coming on top of this slope. Okay? So this is actually the phase that you're going to detect. And you see that it's going to be very annoying, because if I have, in addition to my phase jumps, this phase rotation due to delta F, it's going to make the decoding very difficult. So you must find a way of canceling delta F, the frequency offset between the spaceborne clock and the ground clock. And to do this, there's a clever trick. let us express what is S squared, squaring the signal. That's your exponential of j2 pi delta ft plus j phi squared. Okay, and you all know that this is 2 times the argument. So j2 pi, 2 times delta f t plus j2 phi. But what is 2 phi? 2 times the phase. The phase is equal to 0 pi. So 2 phi is 0 or 2 pi. So by squaring the signal, you cancel the phase modulation. But through energy conservation, where did the energy go? We collapsed all the energy in a carrier, a pure sine wave, at 2 times delta f. So we used to have an information that was spread over 2 megahertz. Your GPS signal is spread over a bandwidth of 2 megahertz. And by taking the square of a signal, you see that we accumulate all the energy in a pure carrier, and this pure carrier is at 2 times delta f. So if you take the Fourier transform, you see 2 times delta f, you divide by 2, you get delta f, and you can cancel out this delta ft and only keep the phase. So this processing, it's not implemented like this, but that's the idea, is actually implemented in a control loop which is called the Costas loop. So the Costas loop is a processing step in GNU Radio that allows you to, this is a demonstration, I take my BPSK signal, if I square it, you get a pure sine wave, and the pure sine wave is at 2 times the initial frequency offset. So let me demonstrate this concept with GNU Radio, just so that you see a little bit what are the consequences of the Costas loop. If I go back to GNU Radio, that's my next example. So in this example, I create a binary phase shift keying. So I take a carrier frequency, 1 kilohertz, sampled at 100 kilosample per second. And you see that I multiply by a square wave, and this square wave is alternatively equal to plus or minus 1. So plus 1, 0 phase, minus 1, pi phase. So when you take a carrier and you multiply with a sine wave, which alternatively is equal to 0 to plus 1 or minus 1, you're creating a BPSK signal. Just for the sake of a demonstration, I'm adding some noise to show you that Costas is resistant to noise. And I run this for a Costas loop. So you will see 3 curves on the output. The first one on the top, over here, will be the direct signal of the BPSK. So on the top here, on channel number 1, the blue one, you will get the output of the multiplication plus the noise, and this is the raw data of the BPSK that you receive with a frequency offset. On the bottom, I just took the square wave, and this square wave is what I actually want. This is a payload. This is what you want to recover. This is the message, the navigation message that was broadcast from the satellite. And on the middle chart here, on the middle curve, you will see the output of a Costas loop. So Costas loop is receiving the signal phase modulated with a frequency offset, and Costas loop will detect the frequency offset, compensate for it, and give you as an output the frequency compensated signal without the frequency offset. So after compensating for delta f. And if you run this flow chart, so first of all, you see that the top one over here is the blue curve. So the blue curve, you see the phase jumps, and the phase jumps are hidden by the fact that the phase is constantly rotating, and because this is a phase, it's between minus pi and pi, so you have a phase wrapping. Okay? So if I change the carrier frequency, so if I change this frequency over here, you see that I can change the delta f, the value left over between the signal that has been broadcast from the satellite and the signal that I'm receiving on the ground. Now, if I look, this is, I told you, the signal that I'm broadcasting. So this is input number 3. Input number 3 is just a square wave. So that's the payload I want to detect. And what is the output of Costas? Well, you see that the Costas loop is doing a very good job at recovering the phase and canceling this frequency offset that you can see on signal number 1. And actually what happens is this is super robust. You see that the red curve is stable whatever the frequency offset I introduce, up to a point where you have too much frequency offset, and you see that the Costas loop is no longer able to recover the payload. You still have a leftover frequency offset. Why is it? Well, remember what in our example here we said we are squaring the signal. So what does squaring the signal mean? It means that if I have a delta f over here, when I square the signal, I'm creating a spectral component at 2 times delta f because I'm squaring. But your discrete time signal processing can only work up to the Nyquist frequency fs over 2. So if you're moving delta f too far to the right, you see that 2 times delta f we've moved to the right twice as fast, up to a point where 2 times delta f might reach the Nyquist frequency and actually get aliased. And if you have an aliasing, of course, the sign is wrong and Costas loop is completely lost. So that gives you a hint as to why, if you have too much of a frequency offset, Costas ends up unlocking. But you see that up to a very good position, it does a good job. And on the negative side, same story. If you alias on the left side, then you can no longer cancel the frequency offset. Okay? So now we went together through all the steps needed for decoding GPS. You understand that we have a pseudo-random sequence. You understand how to generate a pseudo-random sequence. You understand that by correlating, we can extract the signal and improve the signal-to-noise ratio by the pulse compression rate. And you understand that we need to cancel the Doppler shift if we want to be able to detect the phase. So, with all this knowledge, can we actually process some real data? So I wouldn't dare to run acquisition in real time because we know Murphy's law. Chances are that something's going to fail. Probably there is no good satellite where we are here. So I recorded some data for you. If you want to play by yourself, there is a fantastic website by Mark Lichman, which is iqengine.org. iqengine is a repository of samples, data that are uploaded by software-defined radio users. And you will find many, many different types of signals. And in the space over here, you will find some GPS signal, including the one that we're going to use today. So iqengine.org gives you the opportunity, even if you don't have access to a receiver, if you don't have access to a given signal, you have amazing data sets to play with if you want to learn by yourself. So the problem is, okay, I'm going to download data from iqengine.org, but how do I know the organization of the data? Who's telling me what is the bit size, what is the data rate, how is the information organized? And iqengine and the GNU Radio community is promoting a file format where you append to each data set according to the SigMF, so the signal metafile standard, some information that is computer readable that tells you what is the file organization. So what you see here is in the USB stick, this is actually why the image is a bit large. You have a 400 megabyte sample, which is the SigMF data. And next to the SigMF data, we put a meta file. And the meta file holds the meta information that you need in order to be able to analyze the data. So you see the meta file is a JSON compatible file, so it's a computer readable. We don't really care about the carrier frequency because now you understand that the carrier frequency was removed in the analog pre-processing and you only work with baseband signal. So the analog part is gone. What we're interested in is, first of all, what is the sample rate? Because we said Fs, the sampling rate, will determine all the x-axis of your charts. And the second thing we're interested in is the organization of the data. And what you see here is the data type is integer 8-bit complex. So now we know that it's an integer quantity. It's not a floating point number with a mantissa and exponents. We know that each element is 8-bit wide. And we know it's a complex quantity, interleaving real part, imaginary part. So you have I1, Q1, I2, Q2, and so on. So these two lines gives you all the information you need to read the data in GNU Radio. You need to know the sampling rate, you know the file format. So if you go in IQ Engine demo, we start here with a file source. You see that in the file source, we read byte data types because they're 8-bit per sample. We load the data file because it's a large file. We don't care about the meta file at this time now that we understood the organization. And this 8-bit data, actually GNU Radio can read 8-bit integers but assumes that it's going to run processing on floating point numbers. So you need to convert this integer data into interleaved 8-bit samples converted as complex floating point numbers. So this block, icar to complex, is converting the incoming character string, 8-bit stream into complex numbers. We're reading a file, so there is no clock, so we need to put a throttle. And the first thing we can do is look at the spectrum. What is the spectrum of a GPS signal? So I loaded the data, I run this guy, and what you see here is nothing. There's nothing to be seen. I try to tell you GPS is 10 to 20 dB below terminal noise. So all we're sampling here is noise. And actually, if you click on the middle button and you run an averaging, you can average as much as you want. You spread the information over 2 megahertz, and the spread information due to BPSK is well below terminal noise. So you will have a very hard time getting the GPS signal out of the noise. But you might wonder, I'm bothering you for an hour and a half with processing GPS signal. You're not really sure if you understand the processing. And then you're not really sure if I collected data correctly. Did I forget to power the antenna? Did I forget to actually connect the antenna? Is it even worth finishing this lab session and checking if there is some GPS signal in there? What we just said is if we square the signal, we should cancel the phase. So let's square. So when you have gray blocks, it means they're commented out. You can uncomment by plugging in the blocks. So these are the two icons that allow you to unplug or plug, so commenting or uncommenting. So what you do here is you take the data from the GPS signal, you multiply by yourself, so you square. We get rid of the sides of the spectrum, so we low pass filter, and we look at the frequency sink. So we take the Fourier transform. And what you're going to see now is the fact on the bottom chart here, I'm claiming that each one of these spectral components is a satellite. Now, we canceled out the phase, so you cannot say which satellite it is, but at least by seeing these peaks here, you know that we collected satellite signals. It's worth continuing the investigation. I told you that the data are Doppler shifted. But the Doppler shift should have as many satellites rising over the horizon than leaving on the other side of the horizon. Do you have any idea why these peaks are not centered on 0 Hertz? Why is the distribution of these carriers not centered on 0 Hertz? The
receiver?
The receiver oscillator. Here you have something that is mean value 0. As many satellites are rising over the horizon, positive Doppler shift, than setting over the horizon, negative Doppler shift. But this guy is common to all the receivers. So basically what you see here is that I have a poor quality local oscillator, which is offset by about 5 kilohertz. Actually 5 kilohertz on the squared, 2.5 kilohertz on the original signal. Okay? So the mean value of a squared signal tells you what is the frequency offset. Another trick that we can use when we analyze a GPS signal or any repeating signal is the fact that these signals repeat. You don't know what the code is, but you know that it's a CDMA, and if it's a CDMA, you know it's repeating periodically. So if I take the autocorrelation of a signal, so cross-correlation of a signal with a signal, that's the integral of S of t, S star of t plus tau dt, with S equal exponential of j2 pi delta ft plus j phi. And the beauty of autocorrelation is that this is going to be exponential of j2 pi delta ft plus j phi, exponential of complex conjugate, so it's minus the argument. And now it's t plus tau, the second term is t plus tau, minus j phi of t plus tau. And what you see is that this j2 pi delta f t will cancel with this j2 pi delta ft. So these two guys cancel out, and you're left with integral of this exponential of minus j2 pi delta f tau, and you're left with exponential of j phi of t, exponential of j phi t plus tau dt. And this quantity does not depend on time. So the tau value I can take out. So you see that I can take this guy, which does not depend on time, I can take it out of integral. So that would be equal to exponential of j2 pi delta f tau, integral of exponential of j phi of t, exponential of minus j phi of t plus tau. And this quantity here is the cross-correlation of the pattern and the pattern. So this is the autocorrelation of a phase pattern that we broadcast, and we know that the pseudo-random pattern has a correlation. And if I take the magnitude of this thing, the magnitude of this is equal to 1. So you see that the magnitude of the autocorrelation is equal to the magnitude of a pseudo-random sequence. Because you're looking at the safe similarity, and your signal is shifted by the Doppler shift at time t plus tau. So as long as the Doppler shift is not shifting too quickly, the autocorrelation will give you the repetition rate of the chips in the pseudo-random sequence. And to demonstrate the concept and to really prove that we do have satellites in our recordings, what you do is, how do you do the autocorrelation? Now you know perfectly. You take the Fourier transform of the incoming signal. Now we only have one Fourier transform because we multiply conjugate by ourselves. So you take one Fourier transform, multiply conjugate, inverse Fourier transform, and go back to a time domain. And so now if you do the autocorrelation of a signal, what you get is a second proof that there are signals that are worth looking at. This is the power spectrum of your GPS signal. No way to see anything here. This is a squared signal. We have the Doppler shift of each satellite, but we lost the information which satellite it is. And what you see here are the cross correlations at the repetition rate of the GPS signal. Now you might ask, but in the same band there's a Galileo signal as well. Why don't I see the repetition rate of Galileo? Well, because GPS legacy L1 is 1 millisecond long code, and Galileo is 4 times longer, but it's 4 milliseconds. So what you see here is, so zero delay, I'm looking at myself, autocorrelation, GPS, 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 and this is GPS plus Galileo. But they overlap because Galileo is exactly 4 milliseconds and GPS is 1 millisecond. Then GPS, 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 GPS plus Galileo. So actually you cannot separate the various constellations because all the constellations broadcasting in the L1 band are multiple of 1 millisecond code repetitions. So where you have Galileo, Beidou, or GPS, they all have autocorrelation peaks every 1 millisecond. Okay? So now, well, now is the conclusion of this whole story. Is, well, I let you go through in detail at home because there are quite a few blocks. But now that you understood everything, we read the file, we convert from character to complex, we multiply to take the square of a signal just to prove that there are signals. We autocorrelate just to demonstrate that there is signals in there. And then what do we need to do if we want to individually identify each satellite? Well, we need to run the correlation against each satellite pseudo-random sequence for various frequency offsets. And how do you introduce a frequency offset? In GNU Radio, you take the signal and you run it for a frequency translating Fourier filter. So frequency translation is a software implementation of this multiplication with a local oscillator, and you have a frequency transpose signal. So we take the signal, we convert it to floating point numbers, we shift it in frequency, and then, well, then we run correlation with all the copies of the codes, all the copies of the code of a signal that might be there. So because I prepared the lab session, I didn't put all 32 GPS satellites, I didn't put all 32 Galileo signals, I just selected a few GPS signals. I put one Galileo somewhere, there's a Galileo somewhere in there. And what you actually need to do is run exactly the same processing sequence that your GPS receiver would be running, namely search for the Doppler shift that will allow you to correlate energy. So you see in this example, I put a frequency offset of 1.1 kilohertz, and it happens that in this recording, there's two satellites that exhibit a Doppler shift of 1.1 kilohertz, GPS number 29 and the one above, 29 and 25, I remember well, 29 and 28, sorry. So 29 and 28 both exhibit correlation peaks when you frequency offset by 1.1 kilohertz. And what you're seeing, if you look closely, you see that the correlation peaks are slowly shifting in time. That's actually because my local oscillator clock is not finely tuned to the GPS time. So the code rate at which GPS is broadcasting the information is not sampled at exactly the same rate on my software-defined radio. And if you're controlling a GPS DO, if you have a GPS disciplined oscillator, that's exactly what you would be doing. You look at the rate at which the time of your local oscillator is shifting with respect to GPS time, and you would steer your local oscillator so that these correlation peaks stay always at the same place, and that's how you lock your GPS DO on the 1 PPS output. Now, because I prepared the lab session, I can also tell you that there is another satellite that will appear at 3.6 kilohertz. So let's have a quick look at what happens if I shift my local oscillator by 3.6 kilohertz. So if you go here on the top and you replace 1.1 kilohertz with 3.6 kilohertz, it is a bit computation intensive. So it does take a bit of time to refresh, but you should see GPS 25 come out, hopefully. Yes, so there is a bit of lag because my computer is overloaded, but you see that now I shifted to 3.6 kilohertz, and you see GPS 25 correlating, and of course GPS 28 and 29 no longer correlate. And finally, if you want to see Galileo satellite, and I will leave it as an exercise for home to understand how the Galileo signal is working. But just to demonstrate that what I'm providing you as a flowchart is working, on top here you've got Galileo E16, and you see now that the Galileo correlation peaks are more far apart because Galileo is not a repetition interval of 1 millisecond. Galileo is repeating every 4 milliseconds. Okay? So I tried to give you in this lab session all the information needed to understand this somewhat complex flowchart, but I hope that maybe if you're curious enough, you can figure out how all these guys are connecting. It's a lot of copy-paste, but yeah, I try to demonstrate that you can actually decode your GPS information. So it's about time that I conclude. Just the last thing, and then I'm going to let you go to the coffee break. One thing I find amazing with correlation, and it was hinted if you attended yesterday's lecture about power grid surveillance. One thing I found fascinating is you sample at a given sampling rate, so you might think my correlation peak or the resolution of the time delay is determined by the sampling rate. If 1 nanosecond, I need 1 gigahertz. And this is something I prepared for our two-way satellite time and frequency transfer experiment. When we're broadcasting two-way time transfer signals, we are allocated 5 megahertz bandwidth on the satellite. And if we go above the 5 megahertz, Telstar will call us because we're leaking on the neighboring channels. So we have 5 megahertz. 5 megahertz bandwidth is 200 nanosecond period. So you might say the best you can do is measure the time of flight with 200 nanosecond resolution. Your correlation will look something like this. Your autocorrelation, your cross correlation will look something like this. 1 tau at which you get maximum correlation, and all the others you have no correlation. But if you have more than 1 sample per chip, if you oversample a little bit your code, then your cross correlation will look something like this. And as was hinted yesterday, you can do super resolution. And super resolution is as simple as saying I'm running a parabola fit through the correlation peak shape. And what you can demonstrate is that the improvement on the timing capability is equal to the signal-to-noise ratio. So if you have high signal-to-noise ratio, and that is the case with a communication with a geostationary satellite, you can improve your timing capability beyond the sampling period. And to show you this experiment, this is a simulator of a two-way time transfer. We have an FPGA running the pseudo-random sequence, and we're feeding the 2 inputs of a software-defined radio, one of which I add 1 centimeter long SMA extensions. And if you do the calculation, 1 centimeter coaxial cable at 20 centimeter per nanosecond is adding 50 picoseconds. So whenever you're putting an SMA connector, you're adding 50 picoseconds. And what you see here is the time delay that I observe with 0, 1, 2, 3, 4 centimeters. So you see I can measure 50 picoseconds even though I only have 200 nanosecond sampling period. And you might say this is just sheer luck. It's not going to work a second time. Well, you see, I stopped the experiment one evening, I restarted the next morning, it was continuous. I stopped one Friday, I restarted after the weekend, you have a continuity. So no, it's not just sheer luck, it's really the signal processing that works. And if you look at the standard deviation of each one of these measurements, 1 picosecond is over here, 100 femtosecond is over here, because of a high signal-to-noise ratio of directly feeding the FPGA into the SDR, you see that we can get well below the sampling period when you're measuring time of flight. So that's really a beautiful aspect to me of signal processing. And with this, I'm going to conclude this presentation. I wanted to show you how spectrum spreading is at the core of time transfer and time and frequency dissemination. I wanted to show you that using commercial off-the-shelf software-defined radio, you can actually process from the very bottom, from the very IQ stream using GNU Radio, the data that we collected. There's a lot of things you can do additionally. You can have a look at the software we wrote for generating pseudo-random sequences on FPGAs. You can have more fun with additional constellations that you can look at. There's an awesome work by Tomoji Takasu, the author of RTK-lib, who developed the Pocket SDR with my master's students. I reassembled the Pocket SDR. It's 20 euro worth of hardware, and it gives you 40 megahertz, so you can access Galileo or L5. And if you want to do this real-time processing and not post-processing as we did, you've got GNSS SDR, which can be fed the software-defined radio output and real-time process the GNSS, depending on your computational power that you have access to. And with this, I thank you for attention.